Normal distribution. Let's look at the example. A video streaming company collects data on movie downloads by its subscribers. The data shows the average download time for a movie is 14 minutes, with a standard deviation of 4 minutes. Peter's download took 22 minutes, which is considered an unusually long time, but Jack's download took only 8 minutes, a surprisingly fast time. Compare Peter's and Jack's download time in relation to the average time. So let's look at the solution. If we have the mean, the average is 14 minutes, and then we mark 22 minutes 14, we mark 22 minutes of Peter's time. So if this one was 14 and Peter's download time took 22, that means Peter is 8 minutes above the mean, above the average. Okay? And what that means is, if we think that the standard deviation is 4 minutes, so here is 4 minutes and another 4 minutes. So this 8 minutes is nothing else but 2 standard deviation above the mean. So he was 2 standard deviation away from the average. Now, Jack's download time is 8 minutes. So if we mark the 8 minutes on the number line, we see that we are 6 minutes away from the average, from the mean. 6 minutes away. If we look at the standard deviation is 4, and then from 4 another half would be. So the Jack's download time is 1.5 standard deviation away from the mean or below the mean. So if we look at the standard deviations, how many standard deviation, we can compare the two sets to the two data sets. So how many standard deviation away from the mean is nothing else but it's gonna be a concept called the z-score or the standard score. This is the number of standard deviation between the data value and the mean. How far from the data mean the given data value is away. It can be 2 standard deviation, or it can be 1 standard deviation if we're talking about different data, or it could be 1.5 as we have in this example. Now, our data could be above the standard deviation, or it could be below the mean. I mean, our data could be above the mean, or it could be below the mean. So then this number 2 would be the z-score. If you go to the right side, it would be positive. And now if you have to the left side, the z-score would be negative. So let's look at the definition. A z-score or a standard score represents the number of standard deviation a data value is from the mean. So to calculate the z-score, we would use the data value minus the average divided by the standard deviation. So the z-score is equal to my data value, which we call it x, the mean we can call it mu, and standard deviation sigma. The z-score is positive for data value above the mean and would be negative for the data values below the mean. The z-score enables the comparison of quantities by measuring how many standard deviation they are from their respective means, making it possible to compare results across different data sets or different tests. Please note that the z-score of the mean is always 0, because the mean is 0 standard deviation away from the mean. Example 2. 2 runners, Alice and Bob, practice in different distance races. To compare their performance, we use the average finish time and standard deviation for each event. Alice ran a 10K race. The mean finish time is 65 minutes with a standard deviation of 5. Alice finishes in 71 minutes. Now Bob runs a half marathon. The mean finish time is 120 minutes with the standard deviation of 10. Bob finishes in 131 minutes. Relative to their respective events, which runner had the better performance? Which runner was faster? So because we have two different events, two different data sets, we're gonna use the z-score and see how far away from the z-score both data are. So for Alice, so let's keep writing. We have Alice. We have my x, my data point would be 71. So x is 71. My mu is the average, is the mean. This is the mu. That's how we're gonna calculate the z-score. So we look at the average. Average or the mean is 65. And we need standard deviation. Standard deviation, it says, is 5 minutes. So we're gonna have it 5 minutes. Then we can use the z-score formula. Z is equal to x minus mu over standard deviation. We're using this formula right here. So this is equal to 71 minus 65 divided by 5. So this is equal to, if I divide this correctly, 1.2. Now for Bob, we have my x, the data, given data is he finished in 131 minutes. So this is 131. My average mean, or my average or the mean finish time is 120. So this is 120. And standard deviation for the second race is 10 minutes. So if I use the same formula, z-score is equal to x minus mu over sigma. We substitute 131 minus 120 divided by 10. If I calculate this correctly, this coming to 1.1. What does that mean? That means that the Bob finish time is 1.1 standard deviation away from the mean. And that should perfectly make sense, because if we put this on a number line, we're gonna have 120, and then we're gonna have 130, 140, and so the given data is 131. So it's just shortly above 131 is right here. So here is my mean, and standard deviation is 10. So we have 10 and a little bit more. So we have 1.1 above the standard deviation. And the z-score is positive because we are above the standard deviation. Where for Alice's race, we can do exactly the same. We can put the data on a number line. We have 65. We can go 70, 75, 80, 85. We can list it as 1, 2, 3, 4. So in that case, the given data is 71. So we would mark it. 71 is right here. So how far? 5 is the standard deviation, and then a little bit more, some part of the 5. This time is 1 above this one tick, the same as here, but the standard deviation is 10 and here is 5. So this 1 out of 5 is 0.2. So what does it mean? That Alice's finishing time is 1.2 standard deviation away from the average, where Bob finishing time is 1.1 standard deviation above the average. So the better performers closer to the average is no one else but Bob. Just a little better performance has Bob because he's closer to the average than Alice. So Bob has better performance. So now we can talk about normal distribution. It's an arrangement of a data set in which most values cluster in the middle of the range and the rest taper off symmetrically towards either end. A graphical representation of a normal distribution is sometimes called a bell shape because of its flared shape. So if we look at this example, here is the frequency, here is years of number of years a worker works. So here is employees of the cereal factory. So how many years a workers work? 1 year we have 15 people, then 2 years we have 36 people, and so on. So if we look at the shape of data creates so-called the curve that is kind of bell shape. So we say that this data set is normally distributed, because if you think that somewhere here is median, then the average is almost left and right equally distributed. So we call it this shape of normal distribution. For normal distribution, the mean, median, and mode are equal and are located at the highest point. So if we do exact normal distribution, that would be this shape. So we can see that the most frequent would be this, in the middle. And if you calculate the average, you're gonna end up with the same. So the mean, median, and mode is turning out to be exactly the same. For this particular data, they are close to the being bell shape, but we can see that it's not exactly perfectly distributed. So we would have just a little bit a margin of error. But the shape is called normal bell shape, and it's called normal distribution. Now, the area under the bell shape, because if you calculate in percentages, for example, all this data distribution, all of them must add up to being 100%, because that's your total number of data. So the value, the whole area under the bell would be nothing else but 100%, or in decimal it would be up to 1.0. So the total area under the bell is gonna be just 1. Now, properties of normal distribution. A normal curve is bell-shaped, and the highest point on the curve is at the mean of the distribution. So we're gonna have mean at the highest point. The mean, median, and mode of the distribution are exactly the same. The curve is symmetric with respect to the mean, so we have the same symmetry from both sides. The total area under the curve is 1 because it represents the percentage needs to be 100%. Now, for normal distribution, roughly 68% of value are within 1 standard deviation. So if this is my average, then 1 standard deviation away, this gonna be to the right and to the left, total would be 68%. If we roughly divide 68% in half, we're gonna have it 34% on each side, 34% of each side, because that gives us 68%. Now, in other standard deviation, so in other words, one standard deviation, 2 standard deviation. 2 standard deviation, we have almost 95%. So 95% of data are within 2 standard deviation. So we have 2 standard deviation above and 2 standard deviation below. And 99.7% of data values are within 3. So almost all the data are within 3 standard deviation. And this rule is called 68, 95, and 99 rule. So 68, 95, and 99.7 as a rule. So 99.7 is almost 100%. So almost 100% are distributed within 1, 2, 3 standard deviations. So if we break down, as I was saying before, we have total 68%. So if we break down, a 34 would be on one side, and then total is 68. Now this 98%, 95%, we can break down as this 34 already stays, so what's left is 13.5 on each side. If you calculate the total, would be 95%. And then we have 99.7% would be right here, the rest, as it keeps going. So now let's look at example 3. Assume that the distribution has a mean of 10 and a standard deviation of 2. Use the 68, 97, 99.57 rule to find the percentage of values in the distribution that are between 10 and 12. So if I use this shape, what I have right here, my mean would be right in the middle. This mean is 10 because it says so. 10 is right in the middle. Now my standard deviation is 2. So if I go one standard deviation away, 10 plus 2, this value gonna be 12. If I go another standard deviation away, this value plus 2 is gonna be nothing else but 14. And if I go one more standard deviation, this value would be 16. Now, if I go below, standard deviation is 2, so 10 minus 2, this value, data value would be 8. And if I go one more standard deviation away, this data value would be 6. And if I go one more standard deviation, this data value would be 4. So what we have is, this is 1 plus 12, 2 is 12, and so on. So now we can see percentage of data that lie between 10 and 12. Percentage of data that lie between 10 and 12 is nothing else but 34%. So for part A, we have 34% of the data that lie between 10 and 12. 10 is the average. Now, what percentage of data lies above 12? So we have 12 here. Now we can calculate this percentage. What percentage of values lie above? So in that case, we can calculate this by, we know that this total shape is 100%. So half of that would be 50%, right? 50% would be total. And if we subtract the small part, we're gonna get what is above. So we have 3b, so this would be part B. We can redraw the bell shape to show you this clearly. So here is my 10, here is my 12, and I am interested in this area above the 12, right? So we know that this total area is 50%. Now this area, inside this area, is 34%. So how do we calculate the blue area? How do we calculate this area right here? We take 50 minus 34. So we have 50% minus 34%, and that gives me 16%. So what percentage of values are above 12? Above 12, we have 16% of values. And if you want to keep adding 13.5, 2.35, and this one, that should also give you 16%. Now the question is, what percentage, part C, what percentage of values are above 8? What percentage of values are below 8? Below 8 is right here. Below 8. Below 8 would be pretty much nothing else but what we have in the other one as well, right? So if we draw part C, so we would have normal curve. We would have half is 10, one standard deviation is 8, so we're looking for this area below 8. Below 8 is exactly the same because they are symmetrical. Below 8 is exactly the same as this area, right? Because it's symmetrical would be on the other side right here. So this is also 16%. It's exactly the same as part B, except on the other side of the curve. Now, the z-score represents the number of standard deviation a data value is away from the score. So if we look at the bell shape, we can write this bell shape. This is my average. So in terms of z-score, average is zero standard deviations away from the mean. Here is 1, so we're gonna go 1 standard deviation, 2 standard deviation, and 3. So within 68%, we have 1 above and 1 below. So this is the z-score, which is the number of standard deviation away. We use the standard normal distribution table to find the area under this curve between the mean and z-score. The table only gives area for positive z-score, that is, for data that lies above the mean. We use the symmetry of a normal curve to find the areas corresponding to the negative z-score. So right here. So let's see the table. The table is called the standard normal table with the z-score. So the problem is if we are one z-score away, then it's very easy to calculate because we could use the percentages. But how about if you are 1.2, 1.3, 1.5, or something like this? Then you need to have the way to calculate this area, which is the percentage of data. Then we use the tables, call it standard normal table for z-score. So for example, how do we read this one? This table only gives you from 0, from the mean, up to 1, 2, 3 z-scores right here. It only gives you this area. So in order to calculate on the other side, we need to use the properties of the normal distribution. Okay, if I have a z-score of 1.25, how do I use the table? Here is z-score 1.1. We need, 0.1. We need to go to 1.2, and then the next digit be looking at those values. So if we want a 1.2, this area would be 1.21 because I'm adding to this 1.2. The next digit would be 1. That's the next digit. If you need 1.22, you would go to the intersection of this 2. So this is the next digit after this 1.2. And this represents the area 0.388, the area under the curve, or also the probability or percentage of data. But this area only represents from the mean to the right side. So if you have more, always to the right side. So you use the z-scores, so those z-scores. So for example, if we have 1.25, so we're looking 1.2 and going until 5 to get 1.25. So here is my 5. So the intersection of 1.2 is right here. So the area under the curve between 0 and the 1.25 is 0.3944, and it stays so right here. Let's look at some examples. Example 4. Use the standard normal distribution table to find the indicated area. So we have area between 0 and 1.34. So we're looking at the table. We need to go to the z-score 1.3 and then the 4 we're getting from this part. So we're going down to find 1.3 and then we're moving to intersect with the 4. The first 2 digits is right here, and then the last digit 4 or 3 is right on the top. So we're going 1.3 and then we're going intersection to 4. So this is my area. One more time, 1.3. 1.3 is right here, and I'm going through intersection to the 0, 4. So this is the intersection. So this is, I'm looking at this area. So the area would be 0.4099. So this is the area under the normal distribution. This is also probability of how many data lie between 0 and this z-score and how many standard deviation away. We can also change this. We can also change this to percentage. If we multiply simply, if we multiply this by 100% times 100%, we're gonna have the percentage 40.99%. So 40.99% of the data lies under this curve between 0 and 1.3534 standard deviation. So this we can write in percentage 40.99%. Another example, use the standard normal distribution table to find the indicated area. Now we have area to the left. This standard table only gives area to the right, but we know that it's symmetric. So we know that by symmetry, this is gonna be exactly the same area as 1.98, because by symmetry, this area, this shaded area is exactly the same as the area to the right. So we're looking at the table. First, to find z-score 1.9. So on the left side, we look 1.9. And then to find the last digit, we look at the top up to 8. So we look at the intersection of those two. So we have 1.9 right here. And then we're looking until the last digit is right here, so until 8. So that's going to be my intersection up to here, 1.0.8. So this is my area right there. So my area is 0.4761. We can also write this in percentage, that this is 47.61%. This is the area underneath, and that's how we find those values. Example 6. Use the standard normal distribution table to find this indicated area. So we will do as before. We're gonna mark the center to 0, and then we can see that the area to the right is straightforward. We can use the normal table. We're looking at the point 0.83. So 0.8 and intersection of 0.3. So that's gonna be this area to the right. 0.8 and intersection with 0.3. So the area is right here. So the area to the right is 0.2969. That's my area right here, 0.2969. Now, this area to the left, we can do as in the previous example, simply by symmetry. So this area would be exactly the same as right here. So we're looking at the z-score 1.6 and 3. 1.6 and 3 as well, so that's the indicated area. 1.6 and 3 as well. So the area is right here. So this area to the right is 0.4484. So now to find this total area, we simply add those two numbers, right? So we're gonna total area. We have 0.4484 plus 0.2969. And if we add this correctly, we're getting 0.7453. And if we want to write in percentage, that would be 74.53%. Example 6, use the standard normal distribution table to find the indicated area. So now we need to find this area, but the table gives us nothing else but the area to the left. So the table gives us, if we look at that z-score, the table wanna give us this area right here from zero up to this point. So let's find this score for 237. So we're going down 2, 3, and then we coming together with 237. So 2, 3, and we need to get up to 7, 237. So this is the area. So this area is 0.4911. If we did it correctly, cannot see the value down there. Okay, so this is the value right there, 0.911. So now how do we find this area? We can either subtract half. If we take the half, subtract this area, then we're gonna get this stuff, right? Because we know that whole half, this is 0.5 or 50%, because they are equally distributed, right? So our given area, so this area would be 0.5 minus 0.4911, and that gives me 0.0089. Or if we wanna in percentage, we would move 2 decimal to the right, 1, 2. So this is less 0.89%. It's less than 1%. And that should roughly make sense because within 3 standard deviation, all the data lies. So between 2 and 3, it's very small percentage of data there. So in order to solve those type of problems, we're using the properties that half of the area is 50% or 0.5. Total area under the curve is 1. Example 8. Now we need to find the given area up to here. So as before, let's draw the 0. And we know that this area to the left is 0.5. This area we're gonna find from the z table. So we're gonna go 1, 7 up to 8. So let's go. We're going 1, 7, 1.7, and we need to get to intersection of 8. So that's gonna be my score, 0, 7. And we're going until intersection of 8, so it's right here. So this is the z-score. I'm sorry, this is the area, 0.4625. This area is 0.4625. So then the total area or the shaded area would be 0.5 plus 0.4625, and that gives me 0.9625. Or if we wanna in percentage, 96.25%. What that means? That means that within less than 1.78 of standard deviation from the mean, less than lies 96% of the data are right here. We already discussed this, how to formula for converting raw scores to z-score. Assume a normal distribution has mean of mu and a standard deviation of sigma. The following equation converts a value of x into the z-score. So this is the data value, and then we have z-score. Okay, so in example 9, the mean is 100 and standard deviation is 15. And our x is 117. Find the z-score for the given data, and then find the percentage of data that are less than or equal to 117, assuming that the data is normally distributed. So for part A, My mu is 100. That's my mean. Standard deviation, which is sigma, is 15, and my x is 117. Then we use the z-score formula. So the z-score is equal to x minus mu over sigma. So this is 100. Oh, I'm sorry. This is 117 minus 100 over 15. So this gives me 1.13. So my z-score is 1.13. This is how many standard deviation my data is away. So for part B, if I draw the normal distribution bell, here would be my 0, here is my 0, and here is my 1.13, and what percentage of data are less than or equal to this one. So less than or equal to, so that's gonna be to the left. So we're looking for this total area or this total area of that. Now note, we will use normal table in a minute. Now let's maybe use the normal table first to find table gonna give us only this area. So we can use the normal distribution area. Now our z-score was 1.13. 1.1 and 3. So the area is 0.3708 right here. 0. So this area 0.3703 08, I'm sorry, we got it from the table. We know that this area is half 0.5. So my shaded area is gonna be 0.5 plus 0.3708, and that gives me 0.8708. And they ask me what percentage of data. So we have that this is equal to 87.08% of data are less than given data. Now, I would like to point out that on the normal distribution, we can mark as z-scores, or we can mark the given data. So the mean would be 100. Then within 100, the standard deviation would be right here. This would be 115, and 117 is coming exactly up to that spot. 117 data is 1.1 standard deviation away from the given data. Example 9. The mean is 8, standard deviation is 2.4, and x is 6.2. Find the z-score given that the data is normally distributed using normal distribution, and find the percentage of data that are greater than or equal to the 6.2. So let's mark it. Mean. So we have that mu, this is part A. Mu is 8, standard deviation is 2.4, and my data x is 6.2. We use the z-score formula, that z is equal to x minus mu over sigma. So this is equal to 6.2 minus 8 divided by 2.4. And that gives me 6.2 minus 8 is minus 1.8 divided by 2.4. So that gives me minus 0.75. So my z-score is minus 0.75. So that means we are to the left of the standard deviation of the mean. So if we mark this on a normal distribution curve, in the middle is 0, and we are to the left of minus 0.75 to the left. And we ask what percentage of data is greater than or equal. So we're looking what percentage of data is greater than or equal to the given data. As I said before, on the table, we can have it that the mean is 0. So this one is average. This is given data. Then if we subtract 2.4 standard deviation, we would be a little bit, right here is 1 standard deviation. So this difference is 2.4 minus going this direction. So this gives me 6, not even 6, 5.6, right? 5.6 would be the given data. And this would be the -1 on a z-score. So we have two things going on. One is z-scores. Z-scores represent how many standard deviation we are away. And the other thing is actual data. This is my actual data. So if I subtract 2.4, I'm getting 5.6, but my given data is 6.2. So 6.2 represent is right here in this spot. So here is my data 6.2 right here. And 6.2 corresponds exactly to minus 0.75 on the standard deviation. On the z-score, I'm sorry. All right, so then we divide. We know that this half is 0.5. And then this part we need to find by symmetry. This part is exactly the same as we would mark it here, 0.75. Those two would be equal. So we look at the table at 0.75. So 0.70, and we're going up to 5, 0.75. The value is 0.2734. So this area, what we just found it, is 0.2734. So then the given area would be 0.5 plus 0.2734. So in that case, we're gonna have 0.7734. And they ask us for percentage, so it's 77.34%. They ask find the percentage of data. So this is the percentage of data that are greater than 6.2. 6.2 corresponds to z-score minus 0.75. That means we are a little bit less away of 1 standard deviation from the mean. And one more example. The lifespan of a certain type of LED light bulb is normally distributed with the mean of 50,000 hours and a standard deviation of 5,000 hours. What is the z-score corresponding to a light bulb that lasts 44,000 hours? And what percentage of these light bulbs are expected to fail before 44,000? So fail would be less than, because that's the last span, right? All right, so mean is 50. So we're gonna go that the mu, this is part A, mu is 50. Now everything is in thousands, so we can simply just write 50. Then standard deviation is 5. And my given data x would be 44. Then the z-score formula is x minus mu over standard deviation. So we have 50 minus 44 over 5. So this is equal to minus 1.2. So my z-score is minus 1.2. For part B, if I draw the normal distribution curve, I have 0 right in the middle, and minus 1.2 is to the left. This is corresponding to the raw data of 45. This is the raw data of 45. So they ask us that what percentage of bulbs expect to fail. So this is 44,000 lives. So if I go longer, that would be the life, but I fail, that would be to the left. So we're looking for this area to the left. Okay, so by symmetry from normal distribution curve, we can find the area between 0 and this one. Actually, we can find this area, but by symmetry, we will find that area. So we can mark it that this would be this area we can find from the normal distribution curve, and we need to look at 1.2. So 1.2 is right here, 1.2, and we have 0 extra numbers. So 1.2, we have 0.3849. So this area is 0.3849. So we need to find this area. So what we can do, the total area is half, 0.5, right? So we know that the total area is 0.5. So we simply, to find our given area, we simply go 0.5 minus 0.3849, and that gives me 0.1151, and in percentage this is 11.51%. So 11.51% of bulbs are expected to fail before 44,000 hours. Example 12. A factory assembly line measures the time it takes to produce a specific part. The production times are normally distributed with the mean of 12 minutes and a standard deviation of 1.5 minutes. What is the z-score for a part produced in 13.5 minutes? And then part B, use the normal curve to answer these questions. So let's find the z-score first. We know that for part A, the z-score formula is z equal x minus mu over sigma. So in our case, x is the particular data. So x is my data 13.15. So we have 13.5. My mu is the mean. So what is the mean? The mean is 12. So the mean is 12. And my standard deviation is the 1.5. If I substitute all of that to the z-score, I'm getting that it's 13.5 minus 12 divided by 1.5. This is equal to 1.5 divided by 1.5, so this is equal to 1. So my z-score of this particular data is just 1. My z-score of this time 13.5. Now, use the normal distribution curve to answer the question below. What percentage of parts takes less than 13.5 minutes? So we know that this is normal distribution. In the middle we have, right in the middle we have the average, we have the mean, and then we have one standard deviation away from the mean. So this is the mean plus standard deviation, or in other words, this one would be my z-score 1 because it's one standard deviation. At the average, my z-score is 0 or 0 standard deviation away from the mean, right? And at the next part would be my z-score would be 2 right there. So we have the z-score would be 2, and here would be z-score equal to 3. So this corresponds to how far from standard deviation. Z-score is 1, means one standard deviation from the average. So I'm going this way. This would be 2 standard deviation from the average. Now going to the left would be minus 1 because it's to the left to the negative side. So on this part would be minus 1, z-score would be minus 2, z-score would be minus 3. So now, if we have z-score equal to 1, we can use this normal distribution curve, and we know to answer the first question, what percentage of parts takes less than 13.5 minutes? 13.5 minutes z-score is 1, so 13.5, my data would be right here. 13.5 would be my data, and I'm looking for the area that would be less than 13.5, so it's right here. So I need to find all this area. I'm looking for all this area up to this point. Okay, so we know that area to the left, from the right to the left, this area is nothing else but 50%, or we can say 0.5. So now we need to add this little part, and it says that this part is 34%. So we're gonna add to this one this area, which is 34%. So to answer question 1, what percentage of parts takes less than 13.5 minutes to produce, would be 50% whole this part plus 34%. So we have 50% plus 34%. So this gives me 84%. This is the area that is less than. Now they ask me to find for second what percentage would be more than 13.5. More than 13.5 would be the area to the right. In that case, I would simply find, I know that this area is 34, and I know that half of this area is 50%, right? Half of the data normally distributed, is to the right. So it would be 50%, and we subtract 34%. So for second answer would be 50% minus 34%, and that gives me 16%. So what percentage of parts takes more than 13.5% is this area. So this percentage would be 16. If you add all of those ones, you should get also 16%. So in other words, if we have my z-score is exactly 1, not 1.2, not 1.5, if that's exactly 1 or exactly 2, we can use this normal distribution curve that shows the percentages. But if my z-score is fraction 0.8, 1.2, then we use the table that we were using before. So in this table, if you use z-score 1, it's 0.3413, so in other words 34%. So that's exactly the same, 34% for z-score equal to 1.